vertex in this graph. Let me pick this one. Okay, this is some random vertex. I could have picked any other vertex. And let's start tracing a path from here. Okay, let's start traversing the edges of the graph from here, just randomly. Okay, so if there are multiple edges out of any vertex, like for example here there are two possible ways in which we can start. We'll just pick some arbitrary edge and decide to go down along that path. So let me just arbitrarily decide this is going to be the first edge in my path. And again I have three choices here. Let me just randomly pick this edge. I have three choices here, three untraversed edges, so let me pick this one. I have just one untraversed edge, so I don't have any choice here. I'll go along this path. I don't have any choice here now. And now I have a choice, and let's say I go down along this path now. Then again I have a choice. I'm gonna go here this time. Again I have a choice. I'm gonna go like this. And again now I don't have a choice. There's only one edge which is not being traversed, so I go along this edge and I find myself trapped here. Why do I get trapped here? Because I have exhausted all the edges out of this vertex. Now notice that I got trapped at the same vertex from where I started. This will always be true. If we follow such a scheme where we just pick some random vertex and we start tracing some path, the only place where we are going to get trapped is when we return back to that starting point. Why is that true? Because for every other vertex that we visit, if we entered that vertex along an untraversed edge, there must be another unmarked edge out of that vertex which I can always use, because the degree of every vertex is even, right? There are no vertices with an odd degree. The degree of every vertex is even. So every time I mark an edge to enter a vertex, there will be another unmarked edge which will be available for me, by which I can leave that vertex. And the only case where I can get trapped is when I come back to the starting point, because then that's the only way in which I can exhaust. That's the only way I can get trapped, because at the from the starting vertex it's possible that when I have exhausted all the edges of the starting vertex by entering it, I may not now have another edge by which I could leave it. Is this clear? If nobody has any questions here, I'll assume that it's clear. Okay. Now consider the path that we just traced. Is that an Eulerian path? Well, no, because we seem to have left out some of these edges here. Okay, it's possible that we could have traced an Eulerian path, right, by following such a procedure, and if we did, then we are done. But in general, we are going to find that we missed some edges, okay, as in this case. Now, is there a way by which we can extend this path that we just traced to incorporate more edges? So for example, when I don't remember how we traced this, but let's say we traced it like this. We came here and then we came here, then we went like this. Now instead of following this edge, suppose we had traced this triangle and then followed this edge, then we would have used up all these edges. Likewise, when we moved from here, when we traced this edge, instead of going left here, if we had traced this triangle, we would have covered these three edges, and then we would have reached the starting vertex having covered all the edges. Now that's going to be generally true. Whenever this procedure of randomly tracing a path ends up missing some edges, there's one property that's always going to hold. So if you take this original graph and you subtract out the marked edges, okay, look at the graph, look at the original graph with the marked edges deleted. Now such a graph will have just two triangles. Okay, it's going to have two connected components. Now what property holds for this graph? What can you say about the degree of every vertex in this graph, G minus marked edges? The degree of every vertex is still going to be even, right? Because what we traced was a cycle, right? We traced some cycle. The marked edges that we traced make up a cycle, and if we delete this cycle from the original graph, the degree of every vertex will go down only by an even number. And because the degree of every vertex was even at the beginning, when we delete an even number of edges incident on every vertex, we will still have every vertex having an even degree at the end. Okay, so the degree of every vertex will still remain even in this graph. That means we can repeat this same procedure on any vertex inside a connected component to trace another cycle, right? I can start from here, I can trace this triangular cycle and come back at this vertex. Now we have to intelligently decide which vertex to choose as the starting vertex, and in this case what we'll do is we'll choose as our starting vertex some vertex which was incompletely exhausted in our original graph, in our original path, right? This marked path that we traced, it must be the case that there must be some vertices along that path which were not completely exhausted, because the graph is connected. Okay, we are assuming that the graph is connected, otherwise they cannot exist an Eulerian path or a cycle if the graph is not connected. So assuming the graph is connected, if we missed out some edges, what that means is along our marked path there must be some vertices which had edges going out of them that we missed. So choose any such vertex in that along that marked path, and in the subtracted graph start from that vertex and trace another cycle. You should be able to trace another cycle now, because in this graph the degree of every vertex is even. So if you just start randomly walking along the edges, again you will get trapped when you return back to this vertex. Now once you have traced such a cycle, you just take this cycle and stick it into the marked path, the original marked path. So this vertex here was actually this vertex here. So imagine that the portion of the path from the starting vertex up to this point, I'm going to call that as P1. So let's say that portion of the path was P1. Let's say this portion, this cycle that we traced, is C. Okay, and the remaining portion of the path after this vertex in the original path, in the original marked path, was P2. Okay, so the original marked path was P1 and P2. Now what we are doing is we are taking this cycle and sticking it into the middle of that marked path, extending it. Okay, now this is our new marked path. Okay, we start from the starting vertex, we come up to this vertex. So we've traced P1 so far, then we follow this cycle, we trace C, and then we sort of go back along the remaining edges of the original marked path, and this is now our new marked path. Now we check, have we covered all the edges? No, in this case we have missed out this triangle, and we can trace that because we can look at every vertex that we have that our marked path contains and see if it has been exhausted. In this case, this particular vertex is incompletely exhausted. We missed some of the edges out of this vertex. So again, we come up with a subtracted graph, G minus the marked edges, which in this case is just going to be a simple triangle. We start from the vertex which was part of the marked path. So in this case, it's this vertex. and we randomly trace a path. In this case we'll just trace this triangle, and that this becomes our new cycle to be inserted into our marked path that has, along our latest marked path. So this is our latest marked path, sorry, P1C P2. So maybe this path was part of P2, so P2 itself was, let's say, split as P3 and then followed by P4. P3